and it's this function here, which is a function of z is a function of y, which means it's a cylinder in the x direction, right? So x is missing, so it's going to run parallel to the x-axis. It's this exponential cylinder here. And we're going to look at double integral over this region. And this region is defined by, this is a y equals 0. This is y equals natural log of x. This is x equals 1 up here. And so that makes this point right here the intersection of x equals 1 and ln of x. So what value of x, sorry, y equals 1. That's y equals 1. This is y equals 1 here. So what value of x makes y equal to 1? No, what value of x makes, yeah, it gives an ln of 1. So ln of what makes 1?
Professor, why would it be ln 1?
No, yeah, sorry. ln of what gives you 1? That's what I'm asking, sorry, if I misspoke. Yeah, e, right? So ln of e gives 1. So that's, this point is e comma 1. So this is our region. And I can redraw that over here like this. It'll come down the x-axis like that, and then it'll, let's make it a little smaller. It's come down the x-axis like this, and then it'll come out like this, and then it'll head back like this. So maybe something like that. So so that, do you see that that is the same region as this one here? And so I want to integrate, or yeah, do the double integral of this function over the region R. And so first let's talk about what will this compute? Like if we actually do the math and find the final answer, what will that number represent in a context of geometry?
Volume?
Yeah, so it will be volume. This will give the volume. And it's going to be what? The volume of the solid. And what are the characteristics of the solid? What's the top of the solid?
The surface.
The top is the surface, right? The top is f of f, okay? Surface. What's the bottom?
The region.
So, yeah, but we're talking about like the bottom is like going to be a z value, right? So where does the region live, right? So the z value is going to be, bottom is
0.
Yeah, z equals 0, or the xy plane. And then how are the lateral sides defined? So where do the sides of this solid come from?
It's the z values, like the height?
No, the sides, right? So how, the lateral vertical sides, how are they defined?
Isn't it defined by plugging in the x and y values into the equation itself?
No, I'm just talking about the solid. I'm just talking about the solid and how how do we get the sides of the solid, or where do they come from? I'm not talking about doing any math here.
Do you mean that they're all just like vertical planes?
Yep. And where does that vertical, why is it here and not out here or back here or over here?
Oh, that's defined by the region.
Yeah, the region, right? The region, we're extending the edges of the region up in the z direction. And so these give us the walls, right? These give us the sides. So the sides by the perimeter of the region. Does this make sense? So the top of it is the surface, the bottom is the xy plane, and then the sides are defined by the edges of the region, kind of like a cylinder, right? Like that edges of the region are extended up like a cylinder in the z direction. Okay, so, and when we do a double integral, do we always get volume?
You get net volume.
Yeah, right. So in this case, I get volume. Why in this scenario do I get volume, but I don't always get volume?
Z is always greater than 0 here. Because you're not always going to be dealing with measures of length. You're not going to be dealing with physical dimensions always.
No, so I'm asking the question in the geometry context. Okay, so I'm asking the question in the context of geometry. And so the gentleman before said because z is always positive, and that's right. Because the surface is always in positive z territory, all the z values of all the f values of f that we accumulate are going to be positive, and we're going to get volume. But if that surface goes below the xy plane for some xy ordered pairs in the region, then those solids that are carved out below the xy plane in the region, those have a negative contribution to the double integral because these values are negative. So wherever the surface is above the xy plane over the region, you get a positive. Those solids have a positive contribution of their volume. And wherever this surface dips below the xy plane and carves out solids below the xy plane, those solids have a negative contribution of their volume to the double integral. And that's why in general we get what? Net volume, which is a difference of volumes. So that's always correct. So sometimes you get volume, but you can always talk about how you get a difference of volumes from a double integral. Okay. Again, so when the surface goes negative, then in those places that will be the bottom of the solid, and the xy plane will be the top. So the bottom and the top are actually, depending on if f is positive or negative. If f is negative, then the xy plane is the top and the surface is the bottom. And if f is positive, then the surface is the top and the xy plane is the bottom. But the sides are always defined by the perimeter of the region, right? Extended up and down. Okay, questions on meanings, the meaning of the answer of a double integral in the context of geometry. So we talked about that last time and just wanted to review that again. That's super important. Okay, so let's set up the integral to actually find the volume of this one. And we talked last time about how there is so this is again y equals 0, y equals natural log of x. This is E1, and this is y equals 1. Okay, so, and we're doing like this. Okay, so let's do type 1. And type 1 was dy dx, and so that means we do y first. So the mantra is bottom to top, left to right. So dy coming first, we're going to do bottom to top, left to right. And we're going to come along here and look at this and ask, what is the bottom of this region? And we have to consider all the way from the farthest left to the farthest right. So considering the whole span of the region, what constitutes the bottom? And so what we can do is, for the whole span, we're gonna use this analogy that I think is really helpful, is consider an archer down here shooting arrows into the region. And for the bottom, we're asking, where do those arrows pierce into the region? Along what boundary do they pierce into the region? So, what can you say about that?
From 0 to 1. When x is from 0 to 1, y equals 0.
Okay.
And when x is from 1 to e, then it's ln of x.
All right, so he's saying that the bottom is broken up into two different boundaries. There's this part of it is the bottom, but then all of this is part of the bottom too when x is greater than 1 over here. Do the rest of you see that? It's really important. So it's easy to think, oh, the bottom is just this because it's the lowest part of the region. But that's not quite it, because we have to consider the whole span of the region. Where would arrows pierce into this thing for the whole span? Well, sometimes they pierce in that, but sometimes they pierce into the region along that. Does it make sense? So we're going to have to split this up because the bottom is split up. So we're going to have, sometimes the bottom is 0, but sometimes the bottom is ln of x. So we're doing f dy dx. And what about the top? Is that split up, or is that all one boundary?
One.
Always one.
Yeah, it's always, so, and then you think about where the arrows will leave the region. So you're shooting these arrows 3s, sometimes they pierce in y equals 0, sometimes they pierce in y equals ln of x, but they always leave through, for the whole span, they always leave through y equals 1. So sometimes 0 to 1, sometimes natural log of x to 1. Does it make sense? So then our left to right is going to be, the left to right is going to be, where is the bottom 0? So for what x values from left to right is the bottom 0?
From 0 to 1.
0
Yeah,
to 1.
0 to 1. And for what x values is the bottom natural log of x?
1 to e.
1 to e. Does everybody see it? So bottom to top, left to right. And so the left to right has to be broken up according to how the bottom was broken up, right? Sometimes y equals 0 is the bottom. Well, that's true left to right from 0, x equals 0 to 1. Sometimes the bottom is natural log of x. Where? From x equals 1 to e. Questions on the type 1 version of this double integral?
Yeah, Professor, I have a question.
Sure.
I'm a little bit confused here. We see that we have one region here that extends all the way to the surface here of the plane in arrow 3 here. But why is it the integration of this one here is kind of divided into two double integrals?
Because the region, this region here, which is here, the bottom is broken up into two different boundaries. Sometimes the bottom is y equals 0 for x less than 1. For x greater than 1, the boundary is y equals natural log of x. So the bottom of this region, or the least x value, least y value, has two different parts. It has a horizontal line and it has this natural log curve. So horizontal line at 0, natural log curve.
Okay.
Does it help?
Then yeah, that helps a lot. Then what would we want the ln of that one to be? Ask the question in the beginning that what value of the L of x will give the y of 0, and the one student answered that e is going to give that one a 0. So why is it that we want the one to be a 0, the ln of x?
0? The point, the value of e makes ln of e1. That's why this point is e1. It doesn't have to do with 0. I'm not sure how you started talking about this and then you're talking about 0. So I don't understand your question.
Oh no, I was just wondering why we wanted ln of x to be 1 at that point.
Because it's the intersection of y equals 1 and ln of x. We need to get the coordinates of that point. It's the intersection of y equals 1, this top horizontal line, and the equation y equals ln of x is the point E1.
Oh, okay.
So, Professor,
Yeah.
if I may ask as well, so what that does is that essentially, if you look at that context, right, from 1 to e to 1, you have the end of the whole surface, but then at the beginning it's from 0, okay, 0, 0. But then the midpoint right there is 1 to ln of x, is what you're saying? That separates the square from the sort of almost kind of
X equals 1.
right.
X equals 1 is where the bottom boundary changes.
Right.
Yep.
Okay.
And that's shown here. From when x is 0 to 1, the bottom boundary is 0. When x is from 1 to e, the bottom boundary is natural log of x. Okay, let's look at the other way here. Okay, so now type 2 is dx dy, and our mantra now is left to right, bottom to top. So we're going to focus here on the left and the right side, and we're going to see what constitutes the left side. So what constitutes the left side of this? So we look at the whole span, and we fire our arrows in. And where do those arrows pierce into the region? Is it just one boundary or multiple boundaries?
One boundary, x equals 0.
X equals 0, right? Every arrow goes in at x equals 0. And then does every arrow leave the same boundary, or is it on the right side?
No, it leaves at a
No,
different.
it lives in different values.
Different values but the same curve.
Same curve, yeah, different values, but it's the same boundary, right? It's the same curve, which is y equals ln of x is the same as x equals e to the y. So when we go left to right, that's our x coordinate. So all the arrows go in x equals 0, and they all leave e to the y. So this is not split up. We do not have to split up when we go left to right first, because the whole left is 0, and the whole right is e to the y. Does everybody see that? That's our dx.
Can you repeat that one more time, please?
So we're going left to right, left to right. The entire left boundary is x equals 0. There's no change for the whole span of this. And the entire right boundary is also, there's no change. It's this curve.
Okay, thank you.
Yep. And so where does that occur? So then we just have the whole span. Y goes from 0 to 1. So it's not split up. So we're going from 0 to e to the x, e to the y. So like this. So for a given y, we start at 0 and we go to e to the y. It's not the midpoint anywhere, right? So let's say for a given y, we start there and we accumulate across to the left, to the right side. And now we're going to accumulate all those strips starting from the bottom to top. So the first strip's bottom is at 0. The last strip is at 1. So it's like we're going to accumulate like this for the type 2. Questions? So that was easier. Anybody have a question?
So at the point of 1 where we have the between what y equal to 0 between them, see that the curve here is split a bit. We have 0 and then we have e. Now can I still wrap my head around why is the x value, the x's on that one is only passing through actually.
I couldn't really understand your question. Are you talking about type 1 or type 2?
Yeah.
That was an either or. Are you talking about type 1 or type 2?
I'm talking about type 2 here. The one
Type 2? Okay,
left to
so
right, yeah.
type 2 is left to right. The left is always x equals 0. There's no change for the whole span here. Do you see that?
Yes.
And the right, so it's now think of arrows shooting through left to right. The arrows will always enter in x equals 0. They will always exit this curve. There's just this one curve that all the arrows will exit out. And that's x equals e to the y. So the right side is e to the y. Does that answer it?
Yes.
Okay, awesome. All right, let's get to some more examples. So now what we're going to do is I'm going to give you an integral, and the task is to rewrite the integral, the double integral expression, in the other order, right? So it's either going to be given as a type 1 or a type 2, and then you got to create the other one. Okay, so here's the strategy for that. This is called changing the order of integration. Changing the order of integration. Right? Going from either type 1 to type 2, or given type 2, make it a type 1. So the first thing we're going to do is we're going to sketch the region based on the given limits. So you're going to take the limits that you're given and figure out what the region is and make a good picture with all the details. And then you're going to scrap and disregard the limits that were given. Don't ever look at them again. Once you've got the region drawn correctly, that's going to be your focus. Don't go back and focus on the limits. So then you're going to take the region, you're going to do what we just have been doing. So now you've got the good picture with all the details, and you're going to write the other order. So, step 3 is just what we've been practicing so far. Okay, so here's some tips in terms of sketching the region. So in terms of step 1, just kind of what to look out for. So if you have type 1, the focus, the whole ball of wax here, the focus is the top and the bottom. So if you have type 1, dy dx, you're really going to be, your main focus is going to be on that top and that bottom to identify what those are. And that's in terms of the integral being split up or not. Okay? If you have a type 2, then you're going to focus on the creating the entire left and right side for the type 2. That's where your focus is going to be. Okay, and then once you get that right, then the second range of dx for type 1 or dy for type 2, that will fall more into place. Okay, so we're always in drawing the regions, we're focusing on the first heavily, right? That's kind of our heavy focus. All right, let's do these. Now this first one, I want to change the problem. I want to make this from 2 to 5. So instead of 0 to 8, let's see if I can get this right here. I want to change this from, rather than 0 to 8, we're going to do 2 to 5, okay? So here we go. So first of all, what order is this? Is it type 1 or type 2?
1.
Type 1.
This is type 1. So that means that these represent what in the region? 3x represents what boundary of the region, and 24 represents what boundary of the region?
Bottom and top.
Bottom to
respectively.
top. Bottom to top. Y equals 3x is our bottom. Y equals 24 is our top. So we're going to sketch those. Y equals 3x goes through the origin with a slope of 3. Just draw all of y equals 3x. Y equals 24 is a horizontal line. So we know those are going to form our bottom and our top. And now we look between what? Right? Between x equals 2, that's going to be the left, and x equals 5 is going to be the right. So 2. Now we need to know that before we place our 5 here, we need to know where it is relative to this point. So what are the coordinates of this point? The intersection of 3x and 24.
24.
Yeah, so if y is 24, then x has to be 8. So this has an x value of 8 here, so 5 is to the left of it. Okay, so here's 2. That's our left side. 5 is the right side. The top is 24, the bottom is 3x. So do you see what the region is? Bottom 3x, top 24, left 2, right 5. Right there. So there's our region. Okay, and so now we're going to write it as, this is type 1, so we're going to write it as type 2, which is dx dy And we're going to go left to right first, right? Left to right. So here's the span of our region, left to right. Think about shooting the arrows in. Left side, is it just one boundary or split up?
One boundary at y equals 0.
Nope.
Or sorry, no, x equals 2.
X equals
The
2.
boundary,
X equals 2.
yeah,
Then the arrows pierce through, you know, they cruise through the region, and then where do they exit? They're going to exit on the left side. And is that left side going to be one boundary or split up?
split up.
the right side, right?
The right side. So the arrows will pierce in on the left at x equals 2, and they're going to leave the right side where? Through what function?
It's going to be through two functions.
Through two functions, right? These arrows down here at the bottom, they're going to leave out the right side here. And then these arrows up here, they're going to leave out the right side here. So our right side is split up. Does everybody see that? So the left is always 2. The right sometimes is, what, x equals? So we need x equals, so this is going to be x equals 1/3 y. But then sometimes it's going to leave x equals 5. So now we look at what bottom to top, meaning for what vertical ranges do we exit out this y equals, or x equals 1/3 y?
6 to 15.
Right, so if x equals 5, then this point is 5 comma 15 from the 3x. So this is, and this point is 6, right? 6, 15, and 24 are my key y values there. So we exit out the right side 1/3 y when y is between 6 and 15. Left or bottom to top, right? So 6 to 15. And then we exit out x equals 5, the other part of the right boundary, as y goes from 15 to 24. Questions on this?
Wait, where did we get the 6 from?
So I this point right here at x equals 2 is the point at the
Right. Sorry. Got it. Thank
the
you.
bottom, y equals 3x.
Okay, thank you.
Other questions?
How were we able to tell that it was the type 2 instead of the type 1?
Was given as type 1, so we're changing the order to the other one. So we had the type 1, that's how we came up with the picture from the type 1. So then we're going to write it in the other order.
Okay.
Notice when we were writing these limits of integration, we were all about the region and the sketch, not looking back at these numbers, or at these limits. Right? Use the limits to make the sketch, get all the details on your sketch for the region, then use your sketch or region to define the new limits for the other order. Last chance before we go into number 2. Okay, here we go. Gonna erase it. Number 2. So now, given as type 1 or type 2?
Type
Type
2.
2.
We got a type 2. So that means that this is which part of the boundary? So this is x equals y squared. And this is x equals 6, right? Because we're doing dx. What part of the boundary is x equals y squared?
dx left. Yeah, the left. Sorry.
Left, right? So type 2 means left to right, bottom to top. So we're going left to right. So x equals y squared.
Brings in new meaning to code.
Hey, Andrew. Hey, Andrew, your microphone is on? So that's x equals y squared. And we know that's going to be the left side. X equals 6 is going to be the right side. And so now we want to find these points before we go any further. So because where these y limits are, we want to have them correct and relative to these points. So what are the coordinates of that point right there?
Square root of 6.
Coordinates would be x is 6, y is square root of 6. Here x is 6, and y is negative square root of 6. We get that from x equals y squared. So now we're ready to look at the y's, which is bottom to top. So the bottom of this is going to be y equals 0. That's the x-axis. It's the bottom. Therefore, we don't need any of this stuff down here. It's not going to go any lower than that. And the top is y equals radical 6. So where's that relative to this point of intersection? It is that point of intersection, right? So it turns out that the highest most y value is the same as this intersection point. So now we get everything. This is the left side, right side, bottom, up to the highest point will be that point right there. So there's our region. So left to right, bottom to top. And so now we're ready to write it as a type 1, which is bottom to top, left to right. So what's the bottom?
0.
Is it split up or is it all one boundary?
It's all 1.
All one. And then the top. So think of your arrows, right? You think of your arrows like this, all the way across the span of the region. They enter in 0, they exit out 1 or more than one curve.
One curve.
Just one curve, and that's this one. This is the top. So this is y equals what?
Square root of x.
Square root of x. So we're going to go from 0 to square root of x, and then left to right, we're going to start at left here is x equals 0. Right is x equals 6. Done. Questions on that one? Okay, we got one more longer one here. This is a really good example. See if we understand it. I'm going to erase. Here we go. Next one, number 3. So number 3, given as type 1 or type 2?
1.
Given as type 1, that means these are y values here. And it's a sum, right? It's already, so it's given as a sum. And so what's split up here? The bottom split up or the top split up? Boundary. So look, the bottom is always 0. The bottom is always 0.
So it's the top?
The top is split up between, sometimes the top is x plus 1, sometimes the top is that. So x plus 1 has a y-intercept of 1 and slope of 1, like that. There's y equals x plus 1. And this has an intercept of 7, slope of negative a half, so something like this. Okay. This is 7. This is 1. This turns out to be 14 here. This intersection point is, if you set these two equal, you get, I think you get 4, 5. You can check that later, but for time's sake, I just want to get that points 4, 5. Okay, and so when is the top of this thing x plus 1? So the bottom's always 0. The top is x plus 1 from what to what? From 2 to 4. And 4 was our intersection here. So here's 2. So here this is saying the left side is 2, and when you reach 4, that's when that's the end of this boundary, being the top. Okay, and then where is this the top? Well, from 4 to 14, so the whole rest of the way. So we got it. So this is the left side, or this is, so the top is x plus 1 sometimes, negative 1/2 x plus 14 sometimes. Here's our region. Questions on drawing the region? Again, where is it the top? It's the top is x plus 1 when x goes from 2 to 4. That's what we're showing. When x goes from 2 to 4, our top is x plus 1. When x goes from 4 to 14, the top is the other line. So from 4 to 14, top is the other line. So now we're going to rewrite it as type 2, which is dx dy, left to right, bottom to top. So let's look at the left side. Is the left side of this region, is it just one boundary or more than one?
More than one.
I have one vote for more than one.
More than one.
Yeah.
Yeah, right. So it's, the whole span of it is from 0 up to 5. And so if you fire arrows along the whole span into the left side, sometimes those arrows go into x equals 2. Sometimes those arrows go into the region here on y equals x plus 1. So we're going to split it up because the left side is split up. What about the right side?
That's just one boundary.
The right side for the whole span from 5 down to 0 is just this one boundary, the left side. Right side, sorry, right side. Okay, so then we got to get this point right here. What are the coordinates of that point? Well, 2 plugged into x plus 1 is, I think, 2, 3. All right? So that's the point 2, 3. So when is the right side x equals 2? The right side is x equals 2 when y is between
2 and 3. I mean 0 and 3.
0 and 3. When y goes from 0 to 3, that's when our left side is x equals 2. And then when is the left side equal to this right here? As,
3 to 5.
as x goes from, as y goes from 3 to 5, the left side is according to this line. And that's x equals y minus 1. And then what about the right side? We said the right side is the same no matter what y value you're at. This whole thing is just this one right side. And that's our y equals negative 1/2 x plus 14 or plus 7. So we're going to multiply by negative 2. I need to get this as an x value, right? I need to get this as an x value. So negative 2y equals x minus 14. So I think x is minus 2y plus 14. So the entire right side is x equals minus 2y plus 14. So that'll be the top of both double integrals. Whew, made it. Okay, so I went a little briskly there because we got to start the quiz soon. But if I lost you, can you ask me? How'd we do? So notice one thing, that when we did this, it was based on splitting at 4, right? Splitting at x equals 4. But once we switched the order and went the other way from left to right, we did not have to stop at 4. The arrows don't have to come to 4 and stop and then start again. It just goes all the way. It just goes all the way from here to there, and all the way from here to there. So this x equals 4 doesn't play into the type 2. So lots of students in the past have tried to break this up by going from 2 to 4 and then 4 to 14. You don't need to do that. Your left side is here. Your right side is here. Go all the way from the left all the way to the right and just cruise right by x equals 4. Doesn't matter. Questions?